Okay, one important topic in OpenFOAM is boundary conditions. I hope you already get some experience or hands-on experience using or running OpenFOAM. So when you try to run your simulation, maybe you will find overwhelmed with a lot of boundary conditions options. So in this part, I will try to cover a little bit about the boundary conditions. So before we go further, I want you to understand some definitions of Dirichlet and Neumann boundary conditions, which is like become a standard term in the CFD solvers. First, the Dirichlet condition is basically just a fixed value condition specified in the boundary condition. Let's say if we specified some fixed value of temperature, or maybe pressure, or maybe velocity, so that's called the Dirichlet condition. And also we have Neumann condition. I hope I'm not pronouncing it wrong. Neumann, I guess. Or it is like a fixed gradient condition, so we not input some fixed value here. For example, we input like a zero gradient of velocity, so the velocity at that point will be calculated based on the interaction of the flow nearby that point. So it will be zero gradient, for example, or maybe like a fixed gradient which specified let's say pressure gradient in the x direction and anything like that. Then first we want to discuss about the wall boundary condition. For the wall boundary condition, we typically use those no slip conditions, which is basically the same as we input the velocity as 0, 0 and 0 in x, y, z direction. The idea of the no slip condition is that the velocity in the wall itself, or maybe on the wall nearby the zero distance to the wall, is 0, and this creates like a boundary layer like this, and it will be a very special condition to be considered in terms of meshing and also wall function we discussed previously in the turbulent modeling. And for wall boundary itself, it is not only for no slip condition. We can actually input like a slip wall, so the velocity will be the same as the adjacent velocity, or we can actually input the no slip condition with some specified value of velocity. Let's say for our first tutorial, which was the lead driven cavity, we actually input the velocity on the wall, so it will be like driven by the wall movement. Then for the inlet and outlet, which we usually define as patch when we are editing or coding the block mesh. So the patch, we can use the inlet and outlet, and the typical value of the inlet and outlet is like the inlet outlet itself, like say it is like a entrainment or free region, which flow can be go inside the domain or go outside the domain. And we also input fixed value, let's say for the velocity, which is the Dirichlet condition. We can input specific value in the x, y, and z, and in fact we commonly use the uniform value of 0, 0 and something maybe, but we can also actually input other than like uniform value. Let's say if we want to input the fully developed turbulent boundary layer with if we want to simulate a ship like on the sea, which the flow will be have certain boundary layer because of its velocity versus height, you can input it with non-uniform value. And besides of the fixed value of velocity, we can also input the flow rate, inlet velocity, which are which can be defined in the term of the like a volumetric flow in the meter cube per second, or maybe in the mass flow rate in the kilogram per second. So we can actually input this data if you have your like a specific CFM, let's say, for your blower or fan, or maybe your pump have some specific value of mass flow rate. You can input it here. And the other thing is the zero gradient. Actually, we can like input it, like we discussed previously about the zero gradient. Let's say we have like specified constant pressure in inlet. We can define the zero gradient to calculate the velocity, or maybe we can use zero gradient for the pressure if we want to input some specified value of velocity. And it is already discussed in the internal flow. And one other interesting boundary condition is using the fan pressure, which is you can input the fan curve using the table of mass flow rate versus the pressure drop, or maybe the using the head loss, which is always provided in the fan or maybe pump manufacturer. We can input it, so the mass flow rate will be driven by its pressure drop of the system, which is very useful if we don't have any exact value of the constant mass flow rate. And in the inlet, we can also define the turbulent parameters, such as the intensity of the kinetic energy and mixing length, and maybe the boundary layer, inlet and exit, anything like that. Then this is also important thing to consider, which is the free or entrainment boundary condition. So basically, if we are define the entrainment, this location will act as the inlet and at the outlet at the same time. So it will be inflow condition and outflow condition in the same patch. And this is sometimes tricky if we just use some zero zero gradient with constant pressure, let's say, like the outlet pressure. It will be possible for the outlet or outflow, but for the inflow sometimes it is become underpredicted because we don't have any dynamic pressure in it. So sometimes it is beneficial to use the total pressure instead. So we can consider the velocity or dynamic pressure for the entrance flow, but it will be not become an issue if you are just using for the outlet or inlet. So if you use just like a constant pressure, and it will be have some oscillating tendency because of the instability of the dynamic pressure. Then we can also do some domain reduction. Let's say if we want to simulate a whole aircraft, you can actually use the whole aircraft if you want, but if your aircraft is symmetry in the right and the left side, you can divide it by 2 as long as the flow is parallel to the aircraft axis. And it will actually divide your total mesh into 2 regions, which will reduce your computational effort into half. But always remember that if you have like a side slip angle like this, you cannot use this method. Or if you have a non-symmetrical flow like this vortex shedding, of course you cannot use the symmetry. And in OpenFOAM we also have symmetry boundary condition. This is basically just like the zero velocity and the zero gradient for the pressure. Then we can also model our domain into some periodic let's say if we have like a turbine blade which has 3 blades, we can actually divide it into 3 regions and make the periodic plane like this. So the flow going through the point A will be go out from the point B, and from C will go to the point D, etc. So it will be like a 3-dimensional flow. And one thing that is very special about OpenFOAM is it has like lots of boundary conditions. So you can, like find the best for you for your application, and it is like has a lot of flexibilities if you want to use that. But if you already have some basic template for the tutorial folder, you actually doesn't have to worry about these other boundary conditions. But it is a good like a starting point if you want to modify your simulation to certain value. But of course I will not explain it all one by one. Maybe you can take a screenshot from this slide so you can search it as the name. Maybe the name is actually physically like your suitable for your physical condition. Just search it on the OpenFOAM website and it will be some documentation of it. So this is some basic boundary conditions like we discussed previously about the fixed value, zero gradient, fixed gradient. Actually we can also input the fixed gradient and calculate it. It is basically like the solver will not calculate that region, so it will be like calculated. And then for the constraint boundary conditions, we have some cyclic condition, like we use like the periodic. Also we have a symmetry plane. We also have width, which is used like basically like axis symmetry condition for 2-dimensional model. And this is for moving mesh. Also we have some condition. Empty we also often use if we simulate like a 2-dimensional flow. Then inlet boundary conditions. Actually I have 2 slides for this only inlets, because it is very rich. You can find, for example, if you want to make your inlet using the pressure, you can use like a pressure inlet, or if it is like a free stream for external flow, we can also use the free stream, which are the free stream velocity, free stream pressure, and we can input the swirling inlet velocity if you are dealing with local swirling condition. Let's say for the combustion chamber, if you don't want to model the swirler for the geometry and the mesh, you can actually input the swirl inlet velocity to input the, let's say, the rotational velocity and also the tangential and radial velocity, and total pressure like we discussed previously. And turbulent inlet, we also sometimes can input the turbulent value from the inlet. Then for the outlet, it is also the same. You can say check here, let's say wave transmissive, and maybe some total pressure, supersonic free stream, and anything like that, which you can guess from its name that maybe it's matched to your application. You just can type it, Google it, and you will find the description in the OpenFOAM website. This is also the same for the wall boundary conditions, which usually we use the no slip condition and the slip condition, and also moving wall velocity, like our first video. And then We also have a coupled boundary conditions if you want to like map some region to other region. Let's say if we want to use like a bevel velocity, or maybe like map the fixed value, or we have some like a jump and anything like that. But it is sometimes used for the more advanced simulations. And the other generic boundary conditions, like the map field or partial slip condition, like maybe we will not use this lot. In fact, like in my experience using CFD, I will just maybe use like a 10% of this all boundary conditions. So like sometimes we can use the other boundary conditions to have like make the same functionality, but just have some different, like slightly different mathematical properties.